welcome. In this lecture, we're going to talk about, we've been talking about Riemann sums, and that these were going to approximate the area under a curve. And the Riemann sums kind of made more sense to us as to why we would be going from a rate of change to a quantity. And now there's this other notion of the area underneath the curve, which is the definite integral. And so we're going to talk about how we're going to move from the Riemann sum to the definite integral. And then we're also going to connect this up with antiderivatives, not in this lecture, but in the following lectures. So I already wrote this on here, and I'm just going to kind of go through all the pieces of it. I wrote this on here because it's just an accumulation of what you've been seeing in the last lectures. We talked about approximating the area under a curve, y equals f of x, on a particular interval, a, b, and maybe I'll even just kind of add in a little picture here. I just mean something where we've got, right, so the picture to kind of have in mind here is that we have this function y equals f of x. I look at the curve. And then I go ahead and I look at this interval. And I'm interested in this area that's kind of living in, right, underneath the curve. Like that. Okay? And we're able to take, and we did this by dividing it up into pieces and then approximating it with these rectangles. And we used, oops, this should be an n. For some reason, I keep on writing 5 instead of n. Not for some reason, it's because in the first one we used a 5, and then I just keep on writing it, even though my notes always say n. Okay. You may catch me doing that again later, sorry. So we're looking at n subintervals, so we're dividing up this interval from a to b. We're chopping it up into n pieces. And then we're looking at those rectangles that we were doing, right? So then we would look at whether it was the right or the left endpoints. We would get these rectangles that we would then use by finding their area, okay, to approximate the area underneath. And then we wrote out notationally. It looks a little overwhelming at first, but once you kind of unpack it, it's actually not that bad. We kind of notationally wrote out so we could either take our rectangles for each of these subintervals, we could either take from the left-hand side or from the right-hand side to look for the height. If we took for the left-hand side, right, these are always coming from the functions. The only difference, and I kind of highlighted in orange where the differences were, really ends up being where you start and end. And if you're on the left-hand side, you're going to start with this endpoint being plugged into the function. And you're going to end with this endpoint being plugged into the function. But if you're on the right-hand side, you're going to start with this endpoint being plugged into the function and end with this endpoint being plugged into the function. And that's why we get this shift up by 1 from n minus 1 to n, from 0 to 1. So that's where things are different. This f is the function for the curve. And then we just kind of went through, and these were our heights. Plugging into the function gave us our heights. Our widths came from the delta x, which was the width of the subinterval, right? So now, so what's new in this is that the area, so the limit as n goes to infinity. What does it mean as n goes to infinity? It means as we chop finer and finer, our subintervals are getting smaller and smaller, and there are more of them. So the limit as n goes to infinity of Ln equals the area, as long as we're in a nice circumstance, equals the limit as n goes to infinity of Rn. So using the left-hand endpoints and the right-hand endpoints. Okay, so this is kind of important that's coming out of there. Okay, and I'm just going to make a little remark that as long as our function is nice enough. Okay, and then this is going to be that, so now we would have, we can kind of take this. So we took the left and the right endpoints, but we might want to take other points in these subintervals and look at the height there. Okay, so this is kind of new. So the area is going to equal the limit as n goes to infinity of, and then we're going to have the sum from I equals 1 to n of f of xi star delta x. So we still have that this is our height and this is our width. We're just taking it at different points in the interval. Okay, for any sample points, xi star, so I put the star there, it's just any points that I could have chosen in there in this interval. So let's make that a j actually. In the interval where I go from xj minus 1 to xj. Okay, so I could take any point in those intervals, that's going to give me the area. And when this limit exists and is the same for all these choices, so when this limit exists and the same for all choices of xj star, oops, let's consistently make this j. I don't like using i's for indices because it's in complex numbers. It's a real thing. It's a square root of minus 1. When this limit exists and is the same for all choices of xj star, okay, we say that this function f is integrable on this interval AB. Okay, and then we're going to have, so now we get to set up our kind of notation, and then we have, so here we go. So then we write the integral from, and then we're going to go from A to B. Okay, it's going to equal, so now we have our, this is where our function f of x is going to come in, of d of x is going to equal, and it's actually going to equal this limit as our n goes to infinity of the sum of these, right, we're going from j equals 1 to n, so we're chopping it into finer and finer intervals of f of xj star, so I'm allowed to use sample points like this, delta x. Okay, maybe I'll make this in green so it's easier to see. Okay, so we're allowed to, so now this is actually what this is. So there's a few names here of things. So I want to kind of go through and highlight all the, so this is the integral. Oh, and this is called the definite integral of f. So this is the definite integral of, then you want to put in our f from A to B. So this is going to go from A, maybe I can scoot this over and make this whole thing fit in, to B. Okay. Now, so there's a few names for other pieces of this, so let's kind of highlight this. So we've actually gotten to what the integral is. Really, formally, the integral is that limit, okay, as long as that limit exists. That's what's actually going on. And then you're going to hear that it's the antiderivative, but that's actually a theorem of, a fundamental theorem of calculus. But first, So these all have names. Oops, let's do them in red to kind of, I'm going to go through and name everything, but I'm going to do this kind of in red so that we don't, it's easy to see. Don't try to erase with your fingers, erase with the rag. I found a black rag. If you saw this, it looks so much more slick, huh? It's all about looking slick. Okay, so this critter up here, this is called the upper limit. This here is called the lower limit. Because this is where we start, this is where we end. Okay, this critter here is called the integrand. It's just good to know, you know, learn your lingo so that you can communicate. Upper limit, lower limit, integrand. And then this part here, what this really is what happens to your delta x. As you get smaller and smaller and smaller, we turn it into a dx. It's like the infinitely small version. Okay? And you'll notice that this actually look how similar these look. F of x, dx, delta x. Okay, that's something that happens throughout calculus like that. This is like the infinitesimal version, but this is where this is important for you. Okay, this x here tells you what you're integrating with respect to. Okay, what you're varying. So I'm looking at the height for each value of x. I'm considering the height. And then I'm figuring out what's underneath that. Okay? So it's a very important piece. This dx is going to tell you always what you're integrating with respect to, what's varying, and then your function is going to vary as a result of x. And then you're looking at the height over that. Okay? So this is going to be the integral. This is the formal way to say what the integral is. But we're going to be using it a lot, and now you understand where, using your instincts about how things work just from driving and so on, you're going to understand where this comes from and why in the world we're studying it. So I hope that helps you in kind of orienting yourself and understanding what's going on. And so, thank you, and I will see you in the next lecture.